So now what I want to do is I want to emphasize this concept using counters. And the reason why I'm selecting counters is because they're extremely versatile and useful for many applications. And there are many variations of counters that are basically countless and endless counters. But the one we're going to give examples about, or I'm going to follow, are basically a simple binary counter, which just counts, for example, I'm counting here, it's a 4-bit counter. It counts from 0000 all the way to 1111. It could be more bits. It just basically goes from 0 all the way to FFFF, okay? The other one I'm going to talk about, which is a modulo counter. This is actually an extremely practical counter. It doesn't count all the way. So it might be 4 bits, for example, but it doesn't go, for example, the 4-bit here is 15. It doesn't go from 0 to 15. It might go to just to 0 to 8. For some reason, you want to stop it at 8. Usually we use it with timers as well. So it's going to go from 0 all the way to m-1. Okay, that's the modulo counter. So I'm going to construct both of them. So I'm going to Vivado to construct both counters. And what you're going to see is I will start with the code for the register, because it's pretty much the same thing. It's a register. What's a counter? A counter is just a register that can actually add 1 to itself or something. It can actually increase. So I'm going to do that. It's not a universal shift register, so it's not shifting or doing anything, but I'm just going to use it as my starting point. So I'm going to do this in here. I'm just going to add it, and I'm going to create a new file. And that new file, I will call it, for example, binary counter. Let's do that. So it's a system verilog file. So I'm just going to call it binary counter. Okay. I'll do this in here, and then we finish. Okay, so binary counter, we do that in here. Okay, and again, what I'm going to do is I will actually go copy all of this in here, all of this. Okay, even the parameter, I'm just going to copy it. I'm going to say, all right, binary counter, and then we're going to do the following. I'm going to make it my starting point. Okay. All right, it's a binary counter that can go, basically this one, its default value is 8. Clock reset control, I don't need a control anymore. Okay. For example, you can add an enable or whatnot. I'm just, for the sake of simplicity, I'm not going to put enable. Frankly speaking, because I'm not going to load the counter with anything, I don't need that input anymore. Okay, and that's pretty much it. So I have a clock and a reset and some sort of an output for that counter so that I can read it. Okay, so internally, it should always have the next state in the register. It's just, generally speaking, this is good habit to have. The register itself is exactly the same. It's just storing the value of that counter. So I'm just going to keep it as is. And the output, for now, it's basically the same. Whatever you have on the register, this is what I want. Okay, so now what's different is here. So this is what's different. So I'm not doing that shift register anymore. What I'm doing is something else. And that something else is as simple as I'm just adding 1 to the current value. And that's basically it. You're just adding 1. And frankly speaking, you don't even need an always in here. All you need is an assign, is a continuous assignment that tells me, well, the next value should be the current value plus 1. And that's basically it. That's the binary counter. So the binary counter is just a register that, instead of doing all the shift registers and whatnot, the shifts, I'm just doing that. So you see, this is the beauty of the third guideline. Like, it helped me. I figured out that the output logic is the same. Basically the state register is the same. The way I'm storing the state of the system. However, just the next logic is different. I just have to change that, and that's it. So I'm done. So I can basically compile it or synthesize it and implement it and do that. But what I want to do while I'm at it is I want to introduce a very useful concept called a max tick, or some sort of a tick. Okay, so generally speaking, with counters, if you reach the very final value, let's assume for this here it's 8, that means it's the 255, the value decimal 255. Whenever you reach it, usually you want that counter to tell you, hey, I'm done. And usually what we do is we tick for 1 clock cycle. We set some sort of a signal to 1. And let me show you. So that signal, I'm just going to put it in here. I'm going to say, hey, I'm going to say output logic, and I'm going to call it the maximum. Basically, I reach the maximum. And it's a tick because it only lasts for a very short period of time, which is basically the amount of the clock itself. And how do I do this? Well, it's an output, so I'm going to go to the third, which is the output logic, and I'm just going to do my thing in here. I still need to figure out what the value of the register, maybe the counter. Maybe you don't need it, you can remove it, but for now I'm just going to say, for the sake of simplicity, I'm just going to keep it. And it's as simple as saying, okay, the maximum tick can be done in the following manner. So I'm going to say, okay, well, the value of the register, the current value, does it equal 2 to the power n minus 1? Interesting. 2 to the power n, and it's not 9 minus 1, it's 2 to the power n, basically the number of bits. N is here is 8, that means 2 to the power 8 is 256, minus 1 is 255. So I'm asking, is it equal to it? And if it is, I will set that maximum tick to 1, otherwise I will set it to 0. One comment in here is I just want you to know that this is not going to be interpreted as a circuit. 2 to the power is actually not easy to synthesize, and it will not be actually interpreted as a circuit. It will be computed like in a pre-processing step. So I'm going to take that value of 8 and it's going to be replaced. 2 to the power n is actually 256. That's what will be synthesized. Okay, so the power usually here is just something that you do in a pre-processing step. Okay, so now what I want to do is I want to move to the second counter, which is a Modulo M Counter. Again, it counts from 0 to m minus 1, so it's not necessarily the last value that the counter can count to. Okay, so let's go to Vivado and compute or code that. Okay, so in Vivado, what I'm going to do is I'm going to start from the binary counter. Again, I'm going to just copy that code because it's going to be a slight modification of it. So I'm going to copy that code, and then I'm going to go to the modulo counter. I created that file already, and I'll just basically make it my starting point. All right. So the binary counter, we specified how many bits it should count to. As it turns out that the modulo counter, I don't know how many bits it can. Well, I can assume something that really large, but a better way to do it is let's figure out what the value I want that counter to count to. For example, I want it to count to 9, so I wanted to count 10 counts from 0 to 9, which are 10 counts. Okay, so I'm gonna specify this as a parameter. Certain versions of this modulo counter will input it as an input as opposed to a parameter, but I'm just gonna do it as a parameter now. Okay, so let's go through the code, and a counter is a counter, so it needs a clock and a reset. The output logic, we can read the value that is stored inside it, and the maximum tick makes sense because generally speaking these modulo counters are used as timers. This is why you don't want them to actually count towards the end. You just want them to count to a certain number, and then when they reach that number, you know that basically the timer has finished, and you want the maximum tick to be raised, kind of like a flag. Hey, the timer has finished. However, I don't have an n-1 anymore. What I have is I have the number it will actually count to. So what I need to do is I need to figure out how many bits are necessary to get basically up to 9. And if you think about it, I need 10 bits. It's basically the log base 2 of that 10, and that's how we're going to do it. Well, as it turns out, system verilog allows us to actually do, there's a function called c log base of 2, and what I'm going to do is I'm going to make it as an m, and that's basically -1 in here. And what this does, it actually goes and takes that m, puts it in here, compute the log of it, and the log is probably going to be 4, or it's not going to be 4, but it's basically the ceiling of that log. Okay, so the ceiling of that log is going to be 4 because probably the log of 10 is 3 point something. Okay, so that's 4. 4 minus 1 is a 3, so 0 to 3 is 4 bits, and that's enough to actually count toward that number. Of course, when you initialize it to something else, when you instantiate that module and you change the parameter to 100, you will have the exact or the correct number of bits in here. So one comment in here, this is again is a system function. This is anything that starts with a dollar sign is a system function. That means it's not synthesizable. It's not gonna be synthesized. I'm not synthesizing a circuit that actually computes the log. What I'm doing is I'm actually taking that number, whatever it is, I'm taking its log, and then I'm converting that in a pre-processing step. Before it goes through the synthesis and implementation, it actually does this step. Okay, so that's neat. Now what I'm going to do is I'm going to tell you, well, it seems to be useful to keep that number. So what I'm going to do is I'm going to call it as a local parameter, and I'm going to call it the n, and I'm going to say, well, that local parameter should have that value, which is just, it's the same thing. And frankly speaking, I can't put the local parameter before the input and output, okay, because it's just a constant. So I have to repeat it. That's the only way I can do it. And now this n is the same as this n. It has the same meaning. I'm gonna keep it. It's just a counter. A modulo counter is a counter, so it's gonna keep the next reg and reg. It has the same way it operates for the register. And actually, the max tick is a little bit slightly different. We'll get to that. But now I just wanna see the next state logic. So the next state logic is actually, it's not always adding 1, because what I want to do is I want to test what is the current value of this particular counter. Is the current value reg equal to, let's say, 2 to the power m minus 1, or n actually. Actually, I don't need the 2 to the power. Let's see. Is it equal to m minus 1? Did it reach that 9, basically? That's what I'm asking for. Is the current counter, did it reach a 9? In this case, there could be something else. If it did reach 9, what I needed to do is I need to basically reset it. That's the next value. Else, I'm just going to add 1 to it. And that's basically how I change the next state logic. So the next state logic just says the current value, compare it to the value I want to count to, and then if it did reach it, well, the next value is going to be 0. Otherwise, I'm just going to add 1 to it. That's perfect. Okay, so the output logic is pretty much the same. I can just have it. And frankly speaking, I might not need it, so I can actually remove it, the Q in here. I might be able to remove it or whatnot. I'll show you that in a minute. And the maximum tick is almost the same in here. But the maximum tick, I shouldn't actually compute it that way. What I should be computing is actually it's m minus 1. It's the same test. Okay, what if I do not want to, or I don't care about the internal value of the counter, for example? I can actually just take this from the input and output and actually put it somewhere around here. Maybe I can put it right here. And now since I did have already the n, I can just basically, because it's a local parameter, I can just basically say that this is n. It's not an output anymore. And then the rest of the code is the same. It's exactly the same. And especially that this line is just basically make the reg and q synonymous. And that's basically where we store the value. This way, I can use this as a timer that ticks whenever it finishes. And that's about it.